Technology is reshaping the world faster than ever, and 5G Explained helps you make sense of it. We will focus on what it says about mobile and security. Stay with me, the best part is near the end. Chapter 1: Network and Radio. 1. The 5G UE requirements as interpreted from 3GPP-TS. 1. Network functions, NF, and elements of the 3GPP 5G system. 1. The key definitions for the 4G and 5G frame structure and carriers. 2. The key characteristics comparison of the 4G and 5G radio interface. 3. The frequency bands and frequency ranges for the LTE as interpreted FR. For the NR bands and frequency ranges as interpreted from the 3GPP-TS. 5. Some of the key technical specifications of 3GPP New Radio, NR, INTERF. 6. The key technical reports detailing 5G specific radio frequency bands. 2. 5G NR-RAN interfaces as per 3GPP technical specifications. 1. The positioning techniques of the 5G system for locating UE. 2. Functions of the 5G elements for UE positioning. 3. The interfaced in 5G system for positioning services. 2. Description of the security architecture interfaces as presented in FE. For the network functions of 5G taking part to the security procedures. 5. Key terminology related to the mobile subscription. 6. The main stakeholders for standardization of UICC evolution. 1. The principle of the downlink radio link budget. 2. The principle of the uplink radio link budget. 3. Selected models for the 28 GHz scenario. 4. Selected models for the 39 GHz scenario. 5. Selected models for the 60 GHz scenario. 6. Selected models for the 72 GHz scenario. 2. The 5G network deployment's functional elements. 2. The 3G and 4G systems that comply with the ITU requirements for RESP. 3. ITU time schedule for IMT 2020 as interpreted from 9. 4. 3GPP 5G time schedule for Release 15 is aligned with the ITU IMT 202. 5. The contents of this LTE-A deployment handbook. 1. The main phases of the IMT 2020 development by the ITU. Within this. 2. The high-level IMT 2020 process schedule as presented by ITU. 3. As summary of ITU's IMT 2020 requirement categories for 5G. For the 3GPP security requirement categories. 1. Snapshot of some of the most popular commercial mobile communication. 2. The main systems per 3G, 4G, and 5G mobile communication systems co. 3. The main parameter comparison of 3GPP NB IoT modes. 1. High-level snapshot of the mobile network evolution and the support. 2. The key elements of 2G, 3G, and 4G network architecture prior to 5G. Chapter 2: Principle and Architecture. 3. The high-level principle for the architecture of the LTE EPC and 5G. For the 4G EPC develops further for better supporting 5G connectivity. B. 6. The most concrete 5G deployment options summarized. 7. The principle of the 5G NG and U user plane. 3. 10. The comparison of functional elements of the 4G and 5G. Please note. 11. Non-roaming 5G system architecture, presented via service-based int. 12. Reference point presentation of the 5G system architecture for the 13. An example of the 5G architecture in a roaming case, presented using 14. Reference point format of non-roaming 5G system architecture for MU. 15 Reference point format of non-roaming 5G system architecture for CO. 16 Reference point format of the non-roaming architecture for NEF, NET. 17 5G core network architecture for non-roaming via non-3GPP access. 18 non-roaming architecture for interworking between 5G system, 5G new. 20 An example of the mapping of the network slicing components of the 21 The principle of network slices with conceptual examples. 22 The groups A, B, and C to support multiple network slices per DEVIC. 25 The principle of 5G SSC modes as defined by 3GPP. 27 Control and user plane separation, CUPS, as defined by 3GPP. 9. 1 The 5G NR bands as defined in 3GPP Release 15. 2 The frequency band of OFDM as applied into LTE and 5G NR consists of 3 The principle of the OFDM cyclic prefix. 4 Frequency time interpretation of an OFDM signal. 7 The forming of the LTE radio resource block. 8 Mapping of downlink cell-specific reference signals in LTE with norm. 9 2-port MIMO in LTE. The cross indicates the resource elements that 11 The IQ constellation of the QPSK, 4 QAM, and set of other QAM varia. 12 The principle of transmitter block for CP-OFDM. The utilization of 1 The main 5G dimensions supporting a variety of use cases as interper. 2 An example of the distributed cloud concept. For examples of the service outage time. The x-axis represents the uptime. 5 The principle of the service assurance for 5G network slicing. 6 The balancing of resiliency and security as depicted in 10. 7 The difference between legacy and virtualized networks. 8 Principle of NOS CSP as defined in 18. The virtual resources REEF. 15 The interfaces of NRF, which can be divided into home and visited N. 19 The principle of SEP for interconnecting 3GPP networks. Chapter 3. Plane and Control. 21 The protocols for the N1 mode used in 5G SMS delivery. 22A Conceptual example of UDM deployment. 24 The interfaces of UDSF. It is an optional functionality in 5G. 26 The principle of the network slicing in core network deployment. 27 Example of the network slice set and cloud implementation. 30 Comparison of mesh and tree topologies. The latter provides benefit. 31 Conceptual example of 5G transport solution as presented by Ericsson. 32 The protocol stacks for NG and XN interfaces. 33 The high-level 5G user and control plane protocols. 35 The functional split of user plane and control plane in GNB-based O. 36 The control plane protocols of N2 interface. 37 The control plane protocols for the interfaces N2 and N11. 39 The control plane protocols between the UE and AMF. 40 Control plane protocol stack for the communications between UE and 41 The 5GS user plane PDU session protocol structure. The last UPF-RE. 42 Control plane for the scenario prior to the signaling IPsec SA ESTA. 43 The protocol stack of control plane after the signaling IPsec SA is 44 Control plane for establishment of user plane via N3 IWF. 2 5G positioning architecture. There is only one next generation core. 3 Traditional architecture of V2X based on IEEE 802. 11P and other VA. 1. The chain of trust will evolve along with the new variants of the U3 5G building blocks as defined by 3GPP are critical communications, c. 4 security layers as interpreted from SI Malliance. 5 handover between closed and public network. 10 3GPP systems security architecture as interpreted from 3GPP TS33. 11 The 5G security architecture for non-roaming scenario. 12 The 5G key hierarchy as defined by 3GPP in TS. 13 The initial authentication procedure of 5G. 17 The high-level ecosystem for the UICC variants. 18 UICC variants and respective timelines. 19 Potential solution for the IUICC subscription management. 20 A potential IUICC solution based on the tamper-resistant area of TH. 21 Part of the existing architectural components of the system on chip. 22 The potential position of the VPP and other functional elements of. 23 The SSP concept as defined by ETSI TS 103-465V. 1 Evolution of the core network for the LTE EPC, SDN, and NFV. Chapter 4 Mobile and Systems. 2 Principle of the radio link budget parameters. 3 The principle of SUL, supplementary uplink. For examples of 28 GHz link budget cell radius as interpreted from Ref. 5 The achievable data rates per selected distances on 39 GHz band. 2 Co-cited with EUTRA deployment scenario. 5 Standalone deployment scenario for 5G and 4G, referring to respecti. 6 Non-standalone 5G NR and 4G EPS as defined in 3GPP-TR. The A. 7 Option 7 of non-standalone 5G deployment, referred to as Option 7. 8 The non-standalone scenario representing Option 4 and 4A, the latte. 9 Example of logical GNB and EN-GNB deployment. 11 Dual connectivity for non-standalone scenario of EUTRA and new RA. 12 NR and EUTRA, NEDC, scenario referred to as Option 4. 13 Figure NG-RAN and ENDC scenario, NG-ENDC, referred to as OP. 14 Deployment for EPS and 5GS interworking. 15 The comp options as defined in 3GPP Release 12 are still relevant. The 5G Explained presents key aspects of the next, evolved mobile communications system after the 4G era. This book concentrates on the deployment of 5G and discusses the security-related aspects whilst concrete guidelines of both topics for the earlier generations can be found in the previously published books of the author in refs. The 5th generation is a result of long development of mobile communications, the roots of its predecessors dating back to the 1980s when the first-generation mobile communication networks started to convert into a reality. 3. Ever since, the new generations up to 4G have been based on the earlier experiences and learnings, giving the developers a base for designing enhanced security and technologies for the access, transport, signaling, and overall performance of the systems. Regardless of the high performance of 4G systems, the telecom industry has identified a need for faster end-user data rates due to constantly increasing performance requirements of the evolving multimedia. 5G systems have thus been designed to cope with these challenges by providing more capacity and enhanced user experiences that solve all the current needs even for the most advanced virtual reality applications. At the same time, the exponentially enhancing and growing number of IoT, Internet of Things, devices requires new security measures such as security breach monitoring, prevention mechanisms, and novelty manners to tackle the vast challenges the current and forthcoming IoT devices bring along. The demand for 5G is reality based on the major operators' interest to proof the related concepts in global level. Nevertheless, the complete variant of 5G is still under development, with expected deployments complying with the full set of the strict performance requirements taking place as of 2020. As there have been more concrete development and field testing activities by major operators, as well as agreements for the forthcoming 5G frequency allocation regulation by International Telecommunications Union, ITU, World Radio Conference, WRC, 19, this book aims to summarize recent advances in the practical and standardization fields for detailing the technical functionality, including the less commonly discussed security breach prevention, network planning, optimization, and deployment. Aspects of 5G based on the available information during 2018 and basing on the first phase of the Third Generation Partnership Project, 3GPP, Release 15, which is the starting point for the gradual 5G deployment. The term 5G refers to the fifth generation of mobile communication systems. They belong to the next major phase of mobile telecommunication standards beyond the current 4G networks that will comply with the forthcoming International Mobile Telecommunications (IMT) 2020 requirements of ITUR, radio section of the International Telecommunications Union. 5G provides much faster data rates with very low latency compared to the current systems up to 4G. It thus facilitates the adaptation of highly advanced services in wireless environment. The industry seems to agree that 5G is, in fact, a combination of novel, yet to be developed and standardized, solutions and existing systems basing on 4G long-term evolution, LTE, advanced, as well as non-3GPP access technologies such as Wi-Fi, which jointly contributes to optimizing the performance, providing at least 10 times higher data rate compared to current LTE advanced networks, lower latency, including single-digit range in terms of millisecond, and support of increased capacity. Demands for huge amounts of simultaneously connected consumer and machine, or M2M, devices. Because of the key enablers of 5G, some of the expected highly enhanced use cases would include also the support of tactile internet and augmented, virtual reality, which provide completely new, fluent, and highly attractive user experiences never seen before. At present, there are many ideas about the more concrete form of 5G. Various mobile network operators, MNOs, and device manufacturers have been driving the technology via concrete demos and trials, which has been beneficial for the selection of optimal solutions in standardization. This, in turn, has expedited the system definition schedules. While these activities were beneficial for the overall development of 5G, they represented proprietary solutions until the international standardization has ensured the jointly agreed 5G definitions, which, in turn, has led into global 5G interoperability. The mobile communication systems have converted our lives in such a dramatic way that it is hard to imagine communication in the 1980s, when facsimiles, letters, and plain old fixed-line telephones were the means for exchanging messages. As soon as the first-generation mobile networks took off and the second generation proved the benefits of data communications, there was no returning to those historical days. The multimedia-capable third generation in the 2000s, and the current, highly advanced fourth generation offer us more fluent always-on experiences, amazing data rates, and completely new and innovative mobile services. The pace has been breathtaking, yet we still are in rather basic phase compared to the advances we'll see during the next decade. We are in fact witnessing groundbreaking transition from the digital world toward truly connected society that will provide us with totally new ways to experience virtual reality and ambient intelligence of the autonomic IoT communications. The ongoing work on the development of the next big step in the mobile communications, the fifth generation, includes the IoT as an integral part. Although one of the key goals of the 5G is to provide considerably higher data rates compared to the current 4G systems, with close to zero delays, at least an equally important aspect of the new system will be the ability to manage huge amount of simultaneously communicating IoT devices, perhaps thousands under a single radio cell. The term 5G is confusing. During 2016-2017, there were countless public announcements on the expected 5G network deployments while the 4G deployment was still in its most active deployment phase. Up to the third-generation mobile communication networks, the terminology has been quite understandable, as 3G refers to a set of systems that comply with the IMT 2000, International Mobile Telecommunications for 3G, requirements designed by the ITU. Thus, the CTMA 2000, Universal Mobile Telecommunications System, UMTS, High-Speed Packet Access, HSPA, and their respective evolved systems belong to the third generation as the main representatives of this era. The definition of the fourth generation is equally straightforward, based on the ITU's IMT advanced requirements. While 3G had multiple representatives in practice, there are only two systems fulfilling the official, globally recognized 4G category as defined in IMT Advanced, and they are the 3GPP LTE Advanced as of Release 10, and the IEEE 802. 16M referred to also as WiMAX 2. The first 3GPP Release 8 and Release 9 LTE networks were deployed in 2010-2011, and their most active commercialization phase took place around 2012-2014. Referring to ITU terminology, these networks prior to Release 10 still represented the evolved 3G era, which, as soon as they were upgraded, resulted in the fully compatible 4G systems. While 4G was still being developed, the 5G era generated big interest. The year 2017 was a concrete show time for many companies for demonstrating how far the technical limits could be pushed. Some examples of these initiations, among many others, included Verizon 5G Technology Forum, which included partners in the Verizon Innovation Centers, 4, and Qualcomm, which demonstrated the capabilities of LTE Advanced Pro via millimeter wave setup, 5. These examples and other demos and field trials prior to the commercial deployment of 5G indicated the considerably enhanced performance and capacity that the 5G provides. Although fully deployed, Phase 2 of 5G as defined by 3GPP is still set to the 2020 timeframe. As soon as available, the 5G era will represent something much more than merely a set of high-performance mobile networks. It will, in fact, pave the way for enabling a seamlessly connected society with important capabilities to connect a large number of always-on IoT devices. The idea of 5G is to rely on both old and new technologies on licensed and unlicensed radio frequency, RF, bands that are extended up to several gigahertz bands to bring together people, things, data, apps, transport systems, and complete cities, to mention only some. In other words, everything that can be connected. The 5G thus functions as a platform for ensuring smooth development of the IoT, and it also acts as an enabler for smart networked communications. This is one of the key statements of ITU, which eases this development via the IMT 2020 vision. The important goal of 5G standard is to provide interoperability between networks and devices, to offer high-capacity energy-efficient and secure systems, and to remarkably increase the data rates with much less delay in the response time. Nevertheless, the fifth generation still represents a set of ideas for highly evolved system beyond the 4G. As has been the case with the previous generations, the ITU has taken an active role in coordinating the global development of the 5G. There are many ideas about the form of 5G. Major operators and device manufacturers have actively conducted technology investigations, demos, and trials aiming to prove the concepts and contributing to the standardization. There are also several research programs established to study the feasibility and performance of new ideas in academic level. As an example, the European Union, EU, coordinates 5G research programs under various teams. More information about the latest European Commission, EC, funded 5G research plans can be found in EU webpage, which summarizes 5G initiatives. 6. As stated by EU, the 5G of telecommunication systems will be the most critical building block of our digital society in 2020-2030. Europe has taken significant steps to lead global developments toward this strategic technology. Furthermore, EU has recognized that the 5G will be the first instance of a truly converged network environment where wired and wireless communications will use the same infrastructure, driving the future networked society. EU states that 5G will provide virtually ubiquitous, ultra-high bandwidth connectivity not only to individual users but also to connected objects. Therefore, it is expected that the future 5G infrastructure will serve a wide range of applications and sectors, including professional uses such as assisted driving, e-health, energy management, and possibly safety applications. The EC study programs include FP7 Teams and METIS, Mobile and Wireless Communications Enablers for 2020, Information Society, and other internationally recognized entities. One of the international joint activities is the cooperation between EU and Brazil. 7. As for the 5G radio capacity needs on the current bands, the European Commission aims to coordinate the use of the 700 MHz band for mobile services to provide higher speed and higher quality broadband and cover wider areas, including rural and remote regions. The concrete goal of EU is to provide mobile broadband speeds beyond 100 megabits per second. One of the expected key abilities of the 5G networks is the high energy efficiency to cope with a big amount of low-power IoT devices in the field. The benefits include better cost efficiency, sustainability, and widening the network coverage to remote areas. Some of the base technologies for facilitating the low energy include advanced beamforming as well as radio interface optimization via user data and system control plane separation. Other technologies include reliance on virtualized networks and clouds. Chapter 5: Devices and Requirements. The systems also need to be developed at the component level for both networks and devices. Autonomously functioning remote IoT devices require special attention, as they must function reliably, typically several years without human interaction or maintenance. The advances in the more efficient battery technologies are thus in key position. Also, the very small devices such as consumer wearables and M2M sensor equipment may require much smaller electronical component form factors, including tiny wafer-level subscriber modules that still comply with the demanding reliability and durability requirements in harsh conditions. At the same time, the need for enhanced security aspects will require innovative solutions in the hardware, HW, and software, SW, levels. The 5G is a result of a long development of mobile communications, with roots going back to the 1980s when the first-generation mobile communications networks began to be reality. Ever since the first data services, which the 2G system started to include around the mid-1990s, the new generations up to 4G have been based on the earlier experiences and learnings, giving the developers a base for designing enhanced technologies for the access, transport, signaling, and overall performance of the systems. Figure depicts the development of the data rates of the 3G, 4G, and 5G systems. However, the telecom industry has identified a further need for considerably faster end-user data rates to cope with the demands of the evolving multimedia. The 5G could handle these challenging capacity requirements to provide fluent user experiences even for the most advanced virtual reality applications. At the same time, the exponentially growing number of the IoT devices require new security measures, including potential security breach monitoring and prevention. Along with the new M2M and IoT applications and services, there will be role-changing technologies developed to support and complement the existing ones. The 5G is one of the most logical bases for managing this environment, together with the legacy systems in the markets. Although the 5G is still in its infancy until the ITU officially dictates its requirements and selects the suitable technologies from the candidates, the 5G systems will be reality soon. During the deployment and operation of 5G networks, we can expect to see many novelty solutions such as highly integrated wearable devices, household appliances, industry solutions, robotics, self-driving cars, virtual reality, and other advanced, always-on technologies that benefit greatly from enabling 5G platforms. In addition to the traditional type of IoT devices such as wearable devices with integrated mobile communications systems, smartwatch, car communications systems and utility meters, there are also emerging technology areas such as self-driving cars that require high reliability as for the functionality as well as for the secure communications, which 5G can tackle. As next-generation mobile networks, NGMN, states in 8, the 5G will address the demands and business contexts as of 2020 by enabling a fully mobile and connected society. This facilitates the socio-economic transformations contributing to productivity, sustainability, and overall well-being. This is achieved via a huge growth in connectivity and volume of data communications. This, in turn, is possible to provide via advanced, multi-layer densification in the radio network planning and providing much faster data throughput, considerably lower latency, and higher reliability and density of simultaneously communicating devices. In addition, to manage this new, highly complex environment, new means for managing and controlling the heterogeneous and highly energy-efficient environment is needed. One of the major needs is to ensure the proper security of the new 5G services and infrastructure, including protection of identity and privacy. Another aspect in the advanced 5G system is the clearly better flexibility compared to any of the previous mobile communication generations. This refers to the optimal network resource utilization and providing new business models for a variety of new stakeholders. This means that the 5G network functionality will be highly modular, which facilitates cost-efficient, on-demand scalability. In practice, the above-mentioned goals are possible to achieve only via renewed radio interfaces, including totally new, higher frequencies and capacity enhancements for the accommodation of increasing the customer base in consumer markets as well as support for the expected huge amount of simultaneously communication IoT devices. The 5G network infrastructure will be more heterogeneous than ever before, so there will be a variety of access technologies, end-user devices, and network types characterized by deeper multilayering. The challenge in this new environment is to provide to the end users as seamless a user experience as possible. To achieve the practical deployment schedule for the mature 5G initiating the commercial era by 2020, 3GPP as well as supporting entities such as NGMN are collaborating with the industry and relevant standardization organizations covering both traditional teams as well as new, open source-based standardization bodies. As for the security assurance of the new 5G era, there can be impacts expected in the traditional forms of SIM, Subscriber Identity Module, Universal Integrated Circuit Card, UICC, and subscription types, as the environment will be much more dynamic. The ongoing efforts in developing interoperable subscription management solutions that respond in near real time for changing devices and operators upon the need of the users are creating one of the building blocks for the always connected society. It is still to be seen what the consumer and M2M devices will look like physically in the 5G era, but we might see much more variety compared to any previous mobile network generations, including multiple wearable devices per user and highly advanced control and monitoring equipment. Along with these completely new types of devices, the role of the removable subscription identity modules such as SIM UICC can change. The much smaller personal devices require smaller form factors. At the same time, the techniques to tackle with the constantly changing subscriptions between devices need to be developed further, as do their security solutions. The cloud-based security such as tokenization and host card emulation, HCE, as well as the development of the device-based technologies like Trusted Execution Environment, TEE, may be in key positions in the 5G era, although the traditional SIM UICC can still act as a base for the high security demands. One might wonder why yet another mobile communications generation is really needed. In fact, the fourth generation already provides quite impressive performance with low latency and high data rates. The reasons are many-folded. Not only the increasing utilization of the mobile communications networks for ever-advancing applications including higher definition video, virtual reality, and artificial intelligence require much more capacity even in remote areas, and one might argue if even primarily the need is derived from the exponential increase of the IoT devices. The number of the intelligent sensors and other machines communicating with each other, service backends require support for much more simultaneously connected devices. The amount may be, as stated in one of the core requirements of the ITU, 1 million devices per kilometer 2, which outnumbers clearly even the theoretically achievable capacity the advanced 4G can offer. The 5G would thus benefit especially massive IoT development, the increased data rates for consumers being another positive outcome of the new technology. The ITU-R is the highest level authority for defining the universal principles of 5G. The ITU is thus planning to produce a set of requirements for the official 5G-capable systems under the term IMT 2020. As the term indicates, the commercial systems are assumed to be ready for deployment as of 2020. This follows the logical path for ITU-defined 3G and 4G, as depicted in Figure 2. The 3G and 4G systems that comply with the ITU requirements for respective generations. The requirements for 5G are also produced by ITU. So far, 3GPP has made a concrete plan to submit the candidate proposal by 2019. The IMT 2020 is in practice a program to describe the 5G as a next evolution step after the IMT 2000 and IMT Advanced, and it also sets the stage for the international 5G research activities. The aim of the ITU-R is to finalize the vision of 5G mobile broadband society which, in turn, is an instrumental base for the ITU's frequency allocation discussions at the WRC events, from which the WRC 15 was the most concrete session up to date for discussing the 5G frequency strategies. The WRC decides the ways for reorganizing the frequency bands for the current and forthcoming networks, including the ones that will be assigned to the 5G. Concretely, the Working Party 5D, WP5D, of ITU-R coordinates information sharing about the advances of 5G, including the vision and technical trends, requirements, RF sharing and compatibility, support for applications and deployments, and most importantly, the creation of the IMT 2020 requirement specifications. ITU-R WP5D uses the same process for 5G as was applied to IMT Advanced. Specifically for the 5G system evaluation process, the timeline of ITU is the following: Figure 2016-2017. Performance requirements, evaluation criteria, and assessment methodology of new radio, 2018-2020. Definition of the new radio interfaces, 3 ITU time schedule for IMT 2020 as interpreted from 9. While ITU-R is preparing for the evaluation of the 5G candidate technologies that would be compatible with the 5G framework as seen by ITU, one of the active standardization bodies driving the practical 5G solutions is the 3GPP, which is committed to submitting a candidate technology to the IMT 2020 process. The 3GPP is aiming to send the initial technical proposal to the ITU-R WP5D meeting number 32 in June 2019 and plans to provide the detailed specification by meeting number 36 in October 2020. To align the technical specification work accordingly, the 3GPP has decided to submit the final 5G candidate proposal based on the further evolved LTE advanced specifications, as will be their status by December 2019. In addition to the 3GPP, there may also be other candidate technologies seen, such as an enhanced variant of IEEE. As for the 3GPP specifications, 5G will affect several technology areas of radio and core networks. The expected aim is to increase the theoretical 4G data rates perhaps 10-50 times higher, whilst the response time of the data would be reduced drastically, close to zero. The 3GPP RAN TSG, Radio Access Network Technical Specification Group, is the responsible entity committed to identify more specifically these requirements, scope, and 3GPP requirements for the new radio interface. The RAN TSG works in parallel fashion for enhancing the ongoing LTE evolution that belongs to the LTE advanced phase of the 3GPP, aiming to comply with the future IMT 2020 requirements of the ITU. At the same time, the evolved core network technologies need to be revised by the system architecture teams so that they can support the increased data rates accordingly. 3GPP is committed to submitting a candidate technology to the IMT 2020 process based on the following time schedule, as described in the reference SP150149, 5G timeline in 3GPP, Figure June 2019. Initial technology submission by ITU-R WP5D meeting number 32, October 2020. Detailed specification submission by ITU-R WP5D meeting number 36. 3GPP 5G time schedule for Release 15 is aligned with the ITU IMT 2020 Progress 10. As for the development of the security aspects, 3GPP SA3 has produced the 5G security specification TS V15. Some of the most important topics relevant to UICC follow. Tamper-resistant hardware is mandatory for key storage, key derivation, and running the authentication algorithm. Please note that it is not explicitly stated that this applies for both 3GPP and non-3GPP networks and for both primary and secondary authentication. Both Extensible Authentication Protocol, EAP, Authentication and Key Agreement, AKA, and 5G AKA are mandatory to be supported for accessing 5G network using a primary authentication. 4G and 5G AKA are similar with enhancement on the authentication confirmation message. EAP AKA will also be used to access non-3GPP networks. New 5G user identifiers are SUPI, Subscription Permanent Identifier, SUSI, Subscription Concealed Identifier, and 5G GUTI, 5G Globally Unique Temporary Identity. Chapter 6, Standards and Security. As for the radio interface, the most remarkable news of 2017 was the decision to include the 3GPP's 5G Next Radio (NR) work item for the non-standalone mode, for the scenarios with 5G radio base station relying on 4G Evolved Packet Core (EPC). At the same time, there was agreement on Stage 3 for non-standalone 5G NR Evolved Multimedia Broadband (EMBB) includes low latency support. The control plane on EPC ENB user equipment (UE) will be reused. An additional next-generation user plane is adapted on NR-GNB UE. The 3GPP Release 15 was formally frozen on June 2018, meaning that no new work items were accepted into that release. Release 15 thus contains the first phase of 5G and provides the EMBB services for the early markets, either via non-standalone (NSA) or standalone (SA) modes. The ASN 1 notation for the NSA was ready on March 2018, while the ASN 1 for the SA variant was ready September 2018. These notation documents are in practice the implementation guides for the equipment manufacturers, and based on these, the first standard-based lightweight 5G networks were deployed soon after. The second phase of 5G as defined by 3GPP Release 16 with full functionality can be expected to be reality a few months after the freezing of the Release 16 ASN 1 notation set, meaning that the first IMT 2020 compatible 3GPP-based 5G networks will be deployed during 2020. These networks can support also the rest of the 5G pillars in addition to the EMBB, Massive Internet of Things, MIoT, and critical communications referred to as ultra-reliable low-latency communications, URLLC. The following sections summarize some of the key standardization bodies and industry forums that influence 5G either directly or indirectly, as well as the ones dealing with IoT standardization paving the way for the IoT in the 5G era. Global Platform is a standardization body with interest areas covering UICC and Embedded UICC, EUICC, Secure Element, SE, Secure Device, Trusted Service Manager, TSM, Certification Authority, CA, and TEE. The key standards of the global platform related to the IoT include the Embedded UICC Protection Profile, and the body has established an IoT task force. The respective solutions are also valid in 5G, including all the form factors of UICCs, such as embedded and integrated, and their remote management. The organization is outlined in 11, and the respective task forces are listed in 12. The International Telecommunications Union, ITU, is a standardization body with a variety of global telecommunications-related requirements and standards. ITU has a leading role in setting the expectations for the 5G era, and the IMT 2020 requirements are the reference for these performance expectations, 9.13.14. As for the development of IoT, the ITU has an IoT Global Standards Initiative, IoT GSI, established in 2015, as well as a study group 20 on IoT, applications, smart cities, and communities. The aim of the ITU is to ensure a unified approach in ITU-T for development of standards enabling the IoT on a global scale. The key IoT-related standard is the REC. It can be expected that the massive IoT will be a major component of the 5G pillars, along with the EMBB and critical communications, 15. The ITU TSG 20 deals with IoT and its applications, including smart cities and communities, SCNC. The resulting standard is designed for IoT and smart cities. There also is an international standard for the development of IoT, including M2M communications and sensor networks. 16. The IoT GSI concluded its activities in July 2015 following Telecommunication Standardization Advisory Group's TSAG decision to establish the new Study Group 20 on IoT and its applications, including smart cities and communities. All activities ongoing in the IoT GSI were transferred to the SG20. The IoT GSI aimed to promote a unified approach in ITUT for the development of technical standards enabling the IoT on a global scale. ITUT recommendations developed under the IoT GSI by the various ITUT questions, in collaboration with other standards developing organizations, SDOs, will enable worldwide service providers to offer the wide range of services expected by this technology. The IoT GSI also acts as an umbrella for IoT standards development worldwide. 17. The Internet Engineering Task Force, IETF, develops the Internet architecture. The IETF has dedicated IETF Security Area, https://tools. IETF. Org Area Sec Track Wiki. Some of the key standards include the Constrained Application Protocol, CoAP, and adaptation to the current communication security for use with CoAP. There also is the standard for IPv6 Low-Power Wireless Personal Area Network, 6LoWPAN, 18. The IoT directory of IETF is found in 19. 3GPP and its US counterparty 3GPP2 focus on cellular connectivity specifications that have been actively widened to cover also low-power wide area network, LPWAN, area. These include most concretely LTE-M and Category 0 for low bit rate M2M, and the further enhanced terminal categories that are optimized for IoT such as Cat-M1 and NB-IoT. The standardization body also develops security aspects, 2G divided by 3G divided by 4G divided by 5G security principles and architectures, algorithms, lawful interception, key derivation, backhaul security, and SIM-UICC that can give added value for the cellular IoT compared to the competing proprietary variants. 20. The European Telecommunications Standards Institute, ETSI, executes security standardization of UICC and its evolution under the term SSP, Smart Secure Platform. The latter is a continuum that opens room for new forms of UICCs such as embedded and integrated UICCs. The ETSI Technical Committee, TC, M2M is a relevant group for IoT development at ETSI. The organization's overall information can be found at reference 21 and IoT-related program in 22. Furthermore, the ETSI portal of work documents for members is found at 23. The Institute of Electrical and Electronics Engineers, IEEE, 802 series includes aspects for IoT connectivity. There also exist many other related standards useful for IoT environment, like the IEEE STD 1363 series for public key cryptography. The IEEE has many variants from which E11P is designed specifically for vehicle, V2V, communications. That can be considered as a competing technology for the 3GPP-based modes that will be optimized for vehicle communications, especially in the 5G era. 24. The IEEE Project P. 2413 revises IEEE standards for better use within the IoT. The goal of the project is to build reference architecture covering the definition of basic architecture building blocks and integration into multi-tiered systems. The architectural framework for IoT provides a reference model that defines relationships among various IoT verticals, including transportation and healthcare, as well as common architecture elements. It also provides means for data abstraction, protection, security, privacy, and safety. The reference architecture of the project covers the basic architectural building blocks and their ability to be integrated into multi-tiered systems. 25. The task of SIM Alliance is to simplify SE implementation, and it drives deployment and management of secure mobile services. It also promotes SE for secure mobile applications and services and promotes subscription management standardization, which is beneficial to provide a standardized means for the remote management of Embedded Universal Integrated Circuit Card, EUICC, and Integrated Universal Integrated Circuit Card, IUICC, which can be expected to be elemental components of 5G ecosystem. 26. Smart Card Alliance, SCA, has been a centralized industry interface for smart card technology, and it has followed the impact and value of smart cards in the United States and Latin America. As the 5G IoT can be based largely on the basic concept of the SIM card, and thus smart card technology, this task continues being relevant in the 5G era as well. From its inception as the SCA, its current form of Secure Technology Alliance, STA, facilitates the adoption of secure solutions in the United States. The alliance's focus is set on securing a connected digital world by driving adoption of new secure solutions. 27. The GSM Association, GSMA, represents interests of MNOs worldwide. It is involved in the Network 2020 paving the way for 5G. GSMA is involved in the standardization of subscription management and embedded subscriber identity module, ESIM, and their development for M2M and consumer environment. It should be noted that the previous term of GSMA for indicating remote subscriber identity module provisioning, RSP, is now generalized via the term ESIM, which has been approved by the GSMA as a global product label that can be used to indicate that a device is RSP-enabled. 28. The U.S. National Institute of Standards Technology, NIST, develops cybersecurity frameworks to address critical infrastructure including IoT M2M space. The focus is on security and privacy for the evolution of IoT and M2M. It produces Federal Information Processing Standards publications, FIPS pubs. FIPS are developed by the Computer Security Division within the NIST for protecting federal assets such as computer and telecom systems. FIPS 140.13 contains security requirements. The topics on International Technical Working Group on IoT-enabled Smart City Framework of NIST are found in 29, and FIPS pubs are in 30. The National Highway Transportation and Safety Administration, NHTSA, improves safety and mobility on U.S. roadways. It also investigates connected vehicle technology and communications of safety and mobility information to one another. It has International Technical Working Group on IoT-enabled Smart City Framework, 31. The International Organization for Standardization, ISO, International Electrotechnical Commission, IEC, is an elemental body for smart card technology standardization. ISO IEC 7816 and 14400 are SIM UICC standards for contact-oriented and contactless integrated circuit cards, ICCs. There are various solutions in the markets based on these standards, including transport cards, and IoT devices can be expected to be based largely on UICC. ISO IEC 27000 is Information Security Management Framework, which is valid also for IoT security. Related to IoT security, The ISO IEC Common Criteria (CC) is an international security evaluation framework that provides reliable IT product evaluation for the security capabilities based on an international standard, ISO IEC 15408, for computer security certification, which refers to standards denoting EAL, Evaluation Assurance Level, of 1-7. ISO IEC 19794 produces biometric standards, 32. Joint Technical Committee, JTC, 1 is the standards development environment to develop worldwide information and communication technology, ICT, standards for business and consumer applications. Additionally, JTC1 provides the standards approval environment for integrating diverse and complex ICT technologies. ISO IEC JTC1 SC27 deals with IT security techniques, 33. Open Mobile Alliance, OMA, has developed device management, DM. OMA Lightweight M2M aims to optimize the secure communications between all, especially economic, devices. OMA-DM is a subgroup under the OMA Alliance. OMA-DM is an initiative for automotive environment, and it includes over-the-air, OTA, updates for future investigations. The role of OMA is detailed in 34. Conférence Europe en des Postes et des Télécommunications, CEPT, and Electronic Communications Committee, ECC, are coordinated by European Communications Office, ECO. They produce requirements for approval for certification bodies and testing labs. They work in the ECC on smart grids, smart metering, and others under the Ultra-High Frequency, UHF, roadmap. Related to IoT environment, there is an ECC Report 153 on numbering and addressing in M2M communications. M2M can be used in several licensed and unlicensed frequency bands. The aim of ECC is to understand better the spectrum as well as numbering and addressing harmonization needs of existing and future M2M applications, since related initiatives are present in various fora within the ECC, aligning with industry. The Working Group for Frequency Management, WGFM, of the ECC had prepared information to the ECC on the regulatory framework for M2M communications on the basis of frequency bands already available for various M2M usages. See ECC 15, 039 Annex 13, 35. Indirectly related to IoT, North American Electric Reliability Corporation, NERC, is committed to protecting the bulk power system against cybersecurity compromises that could lead to faulty operation or instability. CIP refers to Critical Infrastructure Protection Cybersecurity Standards, the CIP v5 transition program being the most recent one in the United States, 36. Open Web Application Security Project, OWASP, is a worldwide not-for-profit charitable organization focused on improving the security of software. OWASP IoT Project provides information on IoT attack surface areas and IoT testing guides and maintains a top 10 IoT vulnerabilities list, 37. 1M2MS architecture and standards for M2M communications are designed to be applied in many different industries and take account of input and requirements from any sector. It works on e-health and telemedicine, industrial, and home automation, 38. Global Standards Collaboration, GSC, is an unincorporated voluntary organization dedicated to enhancing global cooperation and collaboration regarding communications standards and the related standards development environment. GSC is not a standards development organization and therefore will not develop standards. The members of GSC include ARIB, Association of Radio Industries and Businesses in Japan, ATIS, Alliance for Telecommunications Industry Solutions in the United States, CCSA, China Communications Standards Association, ETSI, IEC, IEEE-SA, IEEE Standards Association, ISO, ITU, TIA, Telecommunications Industry Association in the United States, TSDSI, Telecommunications Standards Development Society in India, TTA, Telecommunications Technology Association in Korea, and TTC, Telecommunication Technology Committee in Japan, 39. Cloud Security Alliance, CSA, is a non-profit organization to promote the use of practices for providing security assurance within cloud computing and provide education on the uses of cloud computing to help secure all other forms of computing. CSA operates the Cloud Security Provider Certification Program, the CSA Security, Trust and Assurance Registry, STAR, a three-tiered provider assurance program of self-assessment, third-party audit, and continuous monitoring, 40. Cloud computing and data centers form an integral part of the 5G infrastructure. Next-generation mobile networks, NGMN, is relevant for overall advanced network technologies as well as for the IoT, 41. As an example, NGMN has launched a project Spectrum and Deployment Efficiencies, URLLC requirements for vertical industries, RAN convergence, and extreme long-range communications for deep rural coverage. These activities are aimed to optimize and guide the telecoms industry toward the successful deployment of 5G beyond 2018. Car-to-Car Communication Consortium, C2CCC, is industry forum for the V2V technology development. It is a non-profit, industry-driven organization initiated by European vehicle manufacturers and supported by equipment suppliers, research organizations, and other partners. The C2CCC is dedicated to the objective of further increasing road traffic safety and efficiency by means of cooperative intelligent transport systems, CITS, with V2V communication supported by vehicle-to-infrastructure communication, V2I. It supports the creation of European standards for communicating vehicles spanning all brands. As a key contributor, the C2CCC works in close cooperation with European and international standardization organizations, 42. The mission of the 5G Automotive Association, 5GAA, is to develop, test, and promote communications solutions, initiate their standardization, and accelerate their commercial availability and global market penetration to address society's connected mobility and road safety needs with applications such as autonomous driving, ubiquitous access to services, and integration into smart city and intelligent transportation. 5GAA offers several levels of membership for corporations, industry organizations, and academic institutions, 43. Chapter 7, Mobile and Requirements. Through open standards and specifications, Trusted Computing Group, TCG, enables secure computing. Some benefits of TCG technologies include protection of business-critical data and systems, secure authentication and protection of user identities, and the establishment of machine identity and network integrity. The work groups are cloud, embedded systems, infrastructure, IoT, mobile, PC client, regional forums, server, software stack, storage, trusted network communications, trusted platform module, TPM, and virtualized platform, 44. InterDigital incorporated designs and develops advanced technologies that enable and enhance mobile communications and capabilities for concept of the living network basing on intelligent networks, which self-optimize to deliver services tailored to the content, context, and connectivity of the user, device, or need. Ecosystem partners providing devices, platforms, and data services, and affiliations include 1M2M, Industrial Internet Consortium, and Convida, 45. This book is designed for the technical personnel of operators, equipment manufacturers, and telecom students. Previous knowledge about mobile communications would help in capturing the most detailed messages of the book, but the modular structure of the chapters, including the introductory part for the technology, is aimed to ensure that the book is useful also for the readers who are not yet familiar with the subject. The readers in mobile equipment engineering, security, network planning, and optimization, as well as application development teams, benefit from the contents, as it details highly novelty aspects of the field, helping in updating the essential information in a compact way. The book is meant primarily for specialists of the field with a need to quickly capture the new key aspects of 5G, important differences compared to previous generations, and the possibilities and challenges in the 5G network deployment. This contents thus demystifies the idea of fifth-generation mobile communications basing on the latest 5G standards and summarizes available information into a compact book form. The book focuses especially on the security aspects as well as on the network planning and deployment of the forthcoming 5G. It summarizes the 5G functionality with a special emphasis on the new security requirements. It discusses the security techniques and gives common-sense guidelines for planning, optimizing, and deploying the networks. Chapters 1-3 of this book form the introductory module that will be useful for both technical and non-technical readers with or without preliminary knowledge about existing mobile communications systems. Chapters 4-7 form the technical description and are directed to the advanced readers with some knowledge on mobile communications, while chapters 8-10 represent the planning module and are meant for seasonal subject matter experts. 5 presents the main level contents of this book to ease navigation between the modules. The modules and chapters are independent from each other, so they can be read through in any preferred order. Nevertheless, if you are starting from scratch, your knowledge of the subject area is less advanced, it is recommended that chapters be read in chronological order. 5. The contents of this LTE-A deployment handbook. This chapter summarizes the technical requirements for fifth-generation 5G systems. It should be noted that this book assumes ITU, International Telecommunications Union, to be the highest authority dictating the minimum 5G requirements. This book thus walks the reader through the explanation of the latest ITU statements for their 5G candidate selection. Furthermore, this chapter summarizes the statements the other relevant standardization body has presented, the Third Generation Partnership Project, 3GPP, being one of the most active stakeholders in the standardization of the 5G. The time schedule for the key aspects of the 5G development and deployment, by the writing of this publication, includes the ITU-RS, the radio section of ITU, high-level requirements presented in the document, 1, and its finalized version, 2. The concrete requirement set for the candidate evaluation have been presented by the end of 2017 as stated in 3. The 3GPP, on the other hand, is one of the most relevant standardization bodies to present a candidate 5G technology for ITU's 5G selection process. The 3GPP has sent the first draft technical specifications as defined in the Release 15 for the preliminary ITU-R review, and the final submission will be based on the frozen technical standard set by Release 16. Other candidate technologies might also be presented to the ITU evaluation, according to the ITU time schedule, although as an example, the Institute of Electrical and Electronics Engineers, IEEE, has not planned to send a complete 5G system proposal to the ITU evaluation. Instead, there will be many IEEE sub-solutions that are relevant in building up 5G networks. This chapter thus introduces new requirements for 5G as far they can be interpreted from various relevant sources. These key sources of information are presented as available now, and based on this information, The requirements are interpreted for the already known and foreseen statements, e via ITU-R, 3GPP, and other entities involved with the standardization of 5G. This chapter also presents the aspects of the interworking of 5G services with legacy systems, presenting general considerations of cooperative functioning of 5G and other relevant systems. Also, the performance aspects of the 5G in fixed and wireless environment are discussed, along with the possibilities and constraints, including the performance in practice now and via expected standardized features. Finally, there is discussion on the impacts of requirements, including impact analysis for the technologies and businesses. With such a variety of 5G announcements for the trial phase as well as the expected 5G deployments, and each press release indicating only limited functionalities and early, preliminary, not yet International Mobile Telecommunications, IMT, 2020 compliant, approaches, one might ask who will dictate how 5G should look. There is obviously great interest in the industry to maintain the competitive edge compared to other stakeholders whilst the global standardization and jointly approved and agreed principles of 5G are still under work. As is customary, ITU has taken the role of defining the mobile communications generations. This was the situation for the third generation, 3G, and fourth generation, 4G, after the success of the first, analog generation, and second, digital generations. ITU defines 3G as a set of radio access and core technologies forming systems capable of complying with the IMT 2000, 3G, and International Mobile Telecommunications Advanced, IMT Advanced, 4G, requirements. Based on the number of end users, Universal Mobile Telecommunications System, UMTS, and its evolution up to Advanced HSPA, High-Speed Packet Access, is the most popular 3G system while Long-Term Evolution, LTE, Advanced, as of 3GPP Release 10, is the most utilized 4G technology. As for the industry, the Next Generation Mobile Network, NGMN, Alliance represents the interests of mobile operators, device vendors, manufacturers, and research institutes. The NGMN is an open forum for participants to facilitate the evaluation of candidate technologies suitable for the evolved versions of wireless networks. One of the main aims of the forum is to pave the way for the commercial launch of new mobile broadband networks. Some practical methods to do this are the production of commonly agreed technology roadmap as well as user trials. So, ITU is still acting as a highest authority to define the global and interoperable 5G requirements for the mobile communications systems in such a way that the requirements are agreed by all the stakeholders. This is to avoid different interpretations by the industry when deploying and marketing the networks. ITU setting the scenery. The practical standardization work results in the ITU 5G compliant technical specifications created by mobile communications industry. One of the most active standardization bodies for the mobile communications technologies is 3GPP, which has created standards for Global System for Mobile Communications, GSM, UMTS HSPA, and LTE Advanced. At present, 3GPP is actively creating advanced standards that are aimed to comply with ITU's 5G requirements. In addition to the 3GPP, many other standardization bodies and industry forums contribute to the 5G technologies. Maybe not complete end-to-end 5G systems are under construction in such a large scale, as is done by 3GPP, but many recommendations by IEEE are used as a base for 5G, as well as any other existing mobile communication technology. The new IEEE recommendations are formalizing the 5G as one part of the complete picture. The ITU recommendation ITU-RM 2083 describes the IMT 2020 overall aspects. It will provide enhanced capabilities, which are much more advanced compared to the ones found in the ITU recommendation ITU-RM. The IMT 2020 has a variety of aspects from different points of view, which greatly extends the requirements compared to previous mobile communication generations. The ecosystem and respective performance are related to users, manufacturers, application developers, network operators, as well as service and content providers. This means that there are many deployment scenarios supported by the IMT 2020 with a multitude of environments, service capabilities, and technological solutions. 1. The ITU represents the highest authority in the field of defining the mobile system generations. The overall vision of 5G, according to the ITU, is presented in 5. In short, the ITU foresees the 5G to function as an enabler for a seamlessly connected society in the 2020 timeframe and beyond. The high-level idea of the 5G is to bring together people via a set of things, data, applications, transport systems, and cities in a smart networked communications environment. The ITU and the respective, interested partners believe that the relationship between IMT and 5G are elements that make it possible to deploy the vision in practice by relying on mobile broadband communications. The idea of 5G was presented as early as 2012 when ITU-R initiated a program to develop IMT for the year 2020 and beyond. As a result, there were research activities established in global environment. The ITU Working Party 5D, WP5D, has been working on the ITU's expected time frame paving the way for the IMT 2020, including the investigation of the key elements of 5G in cooperation with the mobile broadband industry and other stakeholders interested in the 5G. One of the elemental parts of this development has been the 5G vision of the ITU-R for the mobile broadband connected society, which was agreed in 2015. This vision is considered as instrumental and serves as a solid foundation for the World Radio Communication Conference 2019. That will be a major event for the decisions of the 5G frequency bands, including the additional spectrum that will be required in different regions for the massively increasing mobile communications traffic. ITU has played an essential role in the development of mobile radio interface standards. The previous requirements of the ITU ensuring the internationally recognized systems for 3G, IMT 2000, and 4G, IMT Advanced, is now extending to cover 5G via the IMT 2020 requirements. Figure depicts the time schedule of the ITU for the development of the 5G, and for paving the way for the very first deployments as of 2020. 1. The main phases of the IMT 2020 development by the ITU. Within this process, World Radio Conferences 2015 and 2019 play an essential role for extending the 5G frequency band utilization. From various teams considering 5G evolution, one of the most significant is the ITU-R WP5D. It has a role of investigating study areas and deliverables toward IMT for 2020 and beyond via multitude of activities, such as workshops and seminars for the information sharing within the industry and standardization entities. Some of the more specific work item categories include the following: vision and technology trends. These aspects include also market, traffic, and spectrum requirements for the forthcoming 5G era. Frequency band. Investigations focus on frequency band channeling arrangements and spectrum sharing and compatibility. IMT specifications. This item also contains related technical works. Support for IMT applications and deployments. This item addresses the current and future use of international mobile telecommunications, such as the LTE to support broadband public protection and disaster relief, PPDR, communications. The ITU-IMT 2020 requirements form the foundation of the internationally recognized 5G systems. The respective ITU Radio Communications Bureau circular letters work for announcing the invitation for standardization bodies to submit their formal 5G technical proposals for the ITU Working Party 5D evaluation of their compliance with the IMT 2020 requirements. This process follows the principles applied in the previous IMT Advanced for selecting the 4G systems. Prior to the candidate evaluation, the WP5D finalized the Performance Requirements 2017 and formed the evaluation criteria and methodology for the assessment of the IMT 2020 radio interface. After the candidate submission, the WP5D evaluates the proposals during the time of 2018-2020. The work is based on independent, external evaluation groups, and the process is estimated to be completed during 2020, along with draft ITUR recommendation that contains detailed specifications for the new radio, NR, interfaces. Chapter 8. Data and Requirements. The key sources of information for the ITU 5G development can be found in ITU-RM 2083-6, which collects the documents for forming the 5G IMT vision, framework and overall objectives of the future development of IMT for 2020 and beyond. This document contains the recommendations for the future development of IMT for 2020 and beyond, and it defines the framework and overall objectives of the future development considering the roles that IMT could play to better serve the needs of the networked societies. It also includes a variety of detailed capabilities related to foreseen usage scenarios, as well as objectives of the future development of IMT 2020 and existing IMT Advanced. It is based on recommendation ITU-RM. Report ITU-RM. Future Technology Trends of Terrestrial IMT Systems addresses the terrestrial IMT technology aspects and enablers during 2015-2020. It also includes aspects of terrestrial IMT systems related to WRC-15 studies. Report ITU-RM. Technical feasibility of IMT in bands above 6 GHz summarizes the information obtained from the investigations related to the technical feasibility of IMT in the bands above 6 GHz as described in ITU-REC. Recommendation ITU-RM. Framework and overall objectives of the future development of IMT 2000 and systems beyond IMT 2000. Recommendation ITU-RM. Detailed specifications of the terrestrial radio interfaces of IMT Advanced. Report ITU-RM. IMT traffic estimates for the years 2020-2030. Report ITU-RM. Requirements related to technical performance for IMT Advanced radio interfaces. As summarized in the press release, 8. ITU agreed the first 5G requirement set on the 23rd of February, 2017. The ITU's IMT 2020 standardization process follows the schedule plan presented in Figure 2. The high-level IMT 2020 process schedule as presented by ITU. ITU has published the minimum 5G requirements in the document IMT 2020 Technical Performance Requirements, available at 1. The most important minimum set of technical performance requirements defined by ITU provide means for consistent definition, specification and evaluation of the candidate IMT 2020 radio interface technologies, RITs, or a set of radio interface technologies, SRITs. There is a parallel, ongoing development for the ITUR recommendations and reports related to 5G, including the detailed specifications of IMT 2020. As a highest-level global authority of such requirements for a new mobile communications generation, ITU aims, with the production of these requirements, to ensure that IMT 2020 technologies can comply with the objectives of the IMT 2020. Furthermore, the requirements set the goal for the technical performance that the proposed set of RITs must achieve for being called ITU-RS IMT 2020 compliant 5G technologies. ITU will evaluate the IMT 2020 compliant 5G candidate technologies based on the following documents and for the development of IMT 2020. Report ITU-R IMT 2020M Recommendation for Evaluation. Report ITU-R IMT 2020M Recommendation for submission. The recommendation ITU-RM 2083 contains 8 key capabilities for IMT 2020 and functions as a basis for the technical performance requirements of 5G. It should be noted that the key capabilities have varying relevance and applicability as a function of different use cases within the IMT 2020. In summary, the ITU's minimum radio interface requirements include the 5G performance requirements is presented in the next section. More specific test evaluation is described in the IMT 2020 Evaluation Report of ITU-R 9. The peak data rate, BS, refers to the maximum possible data rate assuming ideal, error-free radio conditions that are assigned to a single mobile station with all the available radio resources, excluding the resources for physical layer synchronization, reference signals, pilots, guard bands, and guard times. The term W representing bandwidth, ESP referring to a peak spectral efficiency, the user's peak data rate RP equals WESP. The total peak spectral efficiency is obtained by summing the value per each applicable component frequency bandwidth. This requirement is meant to evaluate the evolved multimedia broadband (EMBB) use case, for which the minimum downlink peak data rate is 20 gigabits per second, whereas the value for uplink is 10 gigabits per second. The peak spectral efficiency, BSHZ, normalizes the peak data rate of a single mobile station under the same ideal conditions over the utilized channel bandwidth. The peak spectral efficiency for the downlink is set to 30 BSHZ, whereas the value for the uplink is 15 BSHZ. The user-experienced UX data rate is obtained from the 5% point of the CDF, cumulative distribution function, of the overall user throughput, correctly received service data units, SDUs, of the whole dataset in Layer 3 during the active data transfer. If the data transfer takes place over multiple frequency bands, each component bandwidth is summed up over the relevant bands, and the UX data rate RUSA equals WES user. This equation refers to the channel bandwidth multiplied by the 5th percentile user spectral efficiency. The ITU requirements for the UX data rate in downlink is 100 megabits per second, whereas it is 50 megabits per second for uplink. 5th percentile user spectral efficiency. The 5th percentile user spectral efficiency refers to the 5% point of the CDF of the normalized user data throughput. The normalized user throughput, BSHZ, is the ratio of correctly received SDUs in Layer 3 during selected time divided by the channel bandwidth. This requirement is applicable to EMBB use case, and the requirement values are, for downlink and uplink, respectively, the following: indoor hotspot, BSHZ, DL, and BSHZ, UL. Dense urban, BSHZ, DL, and BSHZ, UL, applicable to the macro TRXP, transmission reception point, layer of dense urban EMBB test environment. Rural, BSHZ, DL, and BSHZ, UL, excluding the LMLC, low mobility large cell, scenario. Average spectral efficiency can also be called spectrum efficiency, as has been stated in ITU recommendation ITU-RM. It refers to the aggregated throughput, taking into account the data streams of all the users. More specifically, the spectrum efficiency is calculated via the correctly received SDU bits on layer 3 during a measurement time window compared to the channel bandwidth of a specific frequency band divided further by the number of TRXBs, resulting in the value that is expressed in BSHZ TRXP. The ITU requirement values are, for downlink and uplink for eMBB use case, respectively, the following: indoor hotspot 9 BSHZ TRXP, DL, and BSHZ TRXP, UL. Dense urban for macro TRXP layer, BSHZ TRXP, DL, and BSHZ TRXP, UL. The area traffic capacity refers to the total traffic throughput within a certain geographic area, and is expressed in MBSM2. More specifically, the throughput refers to the correctly received bits in layer 3 SDUs during a selected time window. If the bandwidth is aggregated over more than one frequency band, the area traffic capacity is a sum of individual bands. The target value for the area traffic capacity is set to 10 megabits per second per square meter. The user plane latency refers to the time it takes for the source sending a packet in radio protocol layer 2/3 to reach its destination on the respective layer. The latency is expressed in milliseconds. The requirement for the user plane latency is 4 milliseconds for eMBB use case, whilst it is 1 millisecond for ultra-reliable low-latency communications, URLLCs. The assumption here is an unloaded condition in both downlink and uplink without other users than the observed one whilst the packet size is small, zero payload and only Internet Protocol, IP, header. The control plane latency, in turn, refers to the transition time it takes to change from the idle stage to the active stage in URLLC use case. The requirement for the control plane latency is maximum of 20 milliseconds, and preferably 10 milliseconds or less. Connection density refers to the total number of 5G devices that can still comply with the target QoS, quality of service, level within a geographical area which is set to 1 square kilometer, with a limited frequency bandwidth and the number of the TRXBs, the variables being the message size, time and probability for successful reception of the messages. This requirement applies to the Massive Machine Type Communications, MMTCs, use case, and the minimum requirement for the connection density is set to 1 million devices per kilometer too. The high-level definition of the 5G energy efficiency indicates the capability of the RAD. That is the heart of 5G explained. If it helped, a quick subscribe keeps more summaries coming. So how do mobile and security connect? That is exactly where we started. Go back to the top and watch it click into place.